This presentation was prepared for ICDIS 2018 conference. My name is Inas Al-Kashashna. I am a PhD student at IUBUI University. Today I will present a framework for evaluating the quality of static code analysis tools in the context of different software engineering metrics. The framework supports up to 38 software engineering metrics. We applied this framework against both the open source and commercial available static code analysis tool. First of all, we will go through the definition of the static code analysis process. From this slide, we can see that the main goal of static code analysis process is to find the potential defects in the program code without executing the source code. In order to automate this process, the developers and the programmers can use either open source static code analysis tools such as CPP-Check, or they can use commercial static code analysis tool like a CodeSonar. In this research, we try to answer the following research question. The first research question addresses if the developer way of writing the source code will impact the tool's ability to detect the potential defects. The second research question addresses if the software engineering metrics will impact the tool's ability to detect the potential defects. To answer these questions, we proposed a framework to evaluate static code analysis tools. This framework evaluates 2 commercial static code analysis tools and 3 open source static code analysis tools in terms of software engineering metrics. Also, this framework discusses the impact of software engineering metrics on the value of a true positive, false positive, and false negative rate for each static code analysis tool. In the following slides, we will discuss the design of the proposed framework. From this figure, we can note that the proposed framework had been designed as a set of commands such as import, build, export, report, and matrix command. So, in order to evaluate a static code analysis tool, we have to run or execute this command in a specific order. The first command that we will execute is the import command. This command is used to analyze the C++ and Java test cases in order to extract the potential defects from the source code. The extracted defect will be stored on a knowledge base, which will be the output of the import command. The second command that we will execute is the build command. This command allows the framework to run the static code analysis tool either locally or remotely. By the locally, we mean that the developers have to download or install the static code analysis tool in their device in order to run that tool. On the other hand, the proposed framework can run the static code analysis tool remotely using the SWAMP, which is a cloud computing environment supports large number of static code analysis tools. Then the generated warnings will be stored in an actionable knowledge base. This actionable knowledge base will be the output of the build command. The third command that we will execute is the export command, where the output of the import command will be compared with the output of the build command in order to compute the value of the true positive, false positive, and false negative rate for each static code analysis tool. The fourth command that we will execute is the report command. This command will convert the output of the export command into a human-readable format, such as text file. The last command that we will execute is the matrix command. This command will compute the value of software engineering matrix by running the understand static tool, which is an open source tool, uses the source code representation, such as data flow diagram and control flow diagrams, in order to compute the value of software engineering matrix. After that, this command will merge the value of software engineering matrix with the output of import, build, and export command. In this slide, we're gonna discuss the Juliet test suite, which is the test suite that we used in the proposed framework in order to evaluate the quality of static code analysis tool. This test suite has approximately 61,000 C++ or Java test cases. The test suite was created by the National Security Agency in order to assess the quality of a static code analysis tool. I would like to point out that each test case will target exactly only one type of the defect or CWE, which stands for Common Weakness Enumeration. For example, CWE 476 test case will target only a null pointer dereference defect. The warnings that are generated by static code analysis tool can be classified into three different groups: true positive, false positive, and false negative. In this slide, we're gonna discuss the true positive. The warning can be considered as true positive if the tool highlights the known defect in the source code. For example, in this test case, tool 1 detected the stack-based buffer overflow defect, so we can consider this warning as a true positive. While the warning can be considered as a false positive if the static code analysis tool indicates a defect but no defect exists. For example, in this test case, tool 2 highlighted that there is an uninitialized variable defect in the source code, but no defect exists. So we can consider this warning as a false positive. In this slide, we're gonna discuss the false negative. The warning can be considered as a false negative if the tool cannot find the known defect on the source code. For example, in this test case, tool 1 didn't find the CW194 defect, so we can consider this warning as a false negative. In the next slides, we will discuss our experimental results. In this slide, we would like to show you the experimental setup. In order to establish and run the proposed framework, 2 commercial static code analysis tools, 3 open source static analysis tools, C++ and Java Juliet test suite, 38 software engineering metrics, and understand static tool had been used. The 38 software engineering metrics were divided into 3 main groups: volume matrix, complexity matrix, and object-oriented matrix. In general, software engineering metrics are estimated at 3 different levels: project level, file level, and function level. In this research, we estimate the value of software engineering metrics at file and function level. To do that, understand static tool had been used in order to compute the value for the basic count line metric, basic count matrix, basic token matrix, and control flow matrix. In the next slides, we will discuss our experimental results for evaluating static code analysis tools in the term of different software engineering metrics. Due to large number of software engineering metrics we support, we can't include results for each one. We therefore only focus on the ones that yield interesting results that highlight software engineering metrics that can impact a static code analysis tool's ability to correctly identify potential defects in the source code. The rest of the results can be found on the following link. In this slide, we're gonna discuss the behavior of a static code analysis tool based on count output or fan out metric. This object-oriented metric computes the number of output of the function in the source code. The function outputs may be classified into function calls, parameter set, and global variable set. We compute the value for this metric at the function level using understand static analysis tool. This figure highlights the result of a static code analysis tool for CWE 369 divided by 0 error based on the value of the fan-out metric. As shown in this figure, the x-axis shows the true positive rate, while the y-axis shows the value of fan-out metric. On the other hand, the colors in the figure show different type of static code analysis tool. We keep the name of the static code analysis tool confidential because we don't have time to discuss the results with the static code analysis tools vendors. On the other hand, as the value of the count output metric increases, which means the functions in the source code have high degree of coupling, tool 3 finds fewer defects than tool 2 and the other tools. Likewise, tool 2 finds more defects than the other tools when the value of the metric increases. Unfortunately, none of the tools can find any defects in the source code when the value of the metric becomes more than 6. Right, we're gonna discuss the behavior of a static code analysis tool based on the essential complexity metric. Essential complexity is a measure of the source code complexity after iteratively replacing all the well-structured control structures such as if then else and while loop with a single statement. In order to compute the value of essential complexity at a function level, we use the understand static tool. This figure highlights the result of a static code analysis tool for the CWE 762, which stands for mismatched memory management routines based on the value of essential complexity metric. As shown in this figure, the x-axis shows the value of false positive rate, while the y-axis shows the essential complexity metric value. As shown in this figure, tool 2 and tool 3 find more defects than the other tools. We can infer this finding from the low value of the false negative rate for tool 2 and tool 3 when the value of the essential complexity metric increases. On the other hand, tool 4 reports the highest number of false negative warning when the source code has a high value of essential complexity. For example, when the essential complexity value equals 5. Tool 5 and tool 1 take second and third places after tool 4. So, tool 2 can handle the source code that has a high degree of essential complexity better than the other tools. In this slide, we're gonna discuss the behavior of a static code analysis tool based on the count input or fan-in metric. This metric belongs to the object-oriented matrix and computes the number of inputs that the function uses plus the number of the other functions calling the function. The inputs may be classified into global variables that are used in the function and the n parameters. For our experiments, understand compute the value of the software engineering metric at the function level. This figure highlights the result of a static code analysis tool for CWE 457 based on the value of the fan-in or count input metric. As shown in this figure, the x-axis shows the true positive rate, while the y-axis shows the fan-in value. As shown in the figure, the number of uncovered defects or error in the source code by both tool number 2 and tool number 3 decrease as the value of the count input or fan-in increases. Tool number 2 finds more defects or errors than tool number 3 when the source code has a higher degree of fan-in. In other words, when the functions in the given source code have a high number of calling functions and global variables read, Tool number 2 performs better than tool number 3. This slide presented our framework and work on evaluating 5 static code analysis tools in the context of different software engineering metrics that we can measure in the source code. As shown in our results, the performance or quality of the static code analysis tools can be impacted by the value of various software engineering metrics. I would like to point out that choosing a static code analysis tool for a given source code depends on several important factors, such as weakness that the developers want to test for, the value of one or more of the source code metrics, and finally, the structure of the given source code. For example, the static code analysis tool number 2 doesn't perform well with the source code that has a high degree of nuts. Tool number 2, however, performs better when the source code has a high level of coupling. On the other hand, the experimental results show that there is a relationship between the number of uncovered defects by static code analysis tool and the value of the software engineering metrics. So we are planning to use machine learning techniques to predict the performance of a static code analysis tool on a given source code in the term of software engineering metrics. For the future work, we planning to cover more open source static code analysis tool that analyze Python and Ruby. Also, static code analysis tool report a large number of false positive warnings. The manual inspection of the false warnings is a time-consuming and costly process. In the future, we plan to extend the functionality of the proposed framework to address this issue, either by improving the precision of the analysis or by post-processing the false warnings after they are generated. Questions?